Have you ever stopped to think about what's running inside your smart thermostat, or your router, or even the infotainment system in your car? Well, chances are it's Linux, but probably not the version you're used to on a desktop. Today, we are diving deep into the world of embedded Linux, the kind of hidden operating system that powers literally countless smart devices all around us.
I mean, really think about that for a second. How can a tiny little smart camera juggle video streaming, stay connected to your Wi-Fi, and manage file storage, all at the same time on a chip that's maybe the size of your fingernail? Well, the secret sauce is a super customized, highly efficient version of a full-blown operating system. And that's exactly what we're going to unpack today.
So let's start with the basics. What are we actually talking about here? What makes this flavor of Linux so special, and why is it so perfect for these small yet powerful devices?
At its heart, embedded Linux is pretty much what it sounds like. It's the Linux operating system, but it's been carefully trimmed down and tailored. It's built for hardware that has real constraints. Not a lot of memory, very little storage, or maybe some really specific, unique components. The beauty of it is that it brings all those powerful features we expect, like multitasking and networking, to devices that could never dream of running a full desktop OS.
And this table right here, it just lays the differences out so clearly. On your desktop, you've got gigabytes of RAM and huge hard drives. But in an embedded system, every single megabyte counts. I mean, that directly translates to cost and power draw, which is a huge deal when you're making millions of these things. And check out boot time. Your PC can take its sweet time, but a car's backup camera, that has to be on like now. It is all about efficiency and building something for one specific purpose.
So, here's the key takeaway. Embedded Linux really gives you the best of both worlds. You get the robust, time-tested features of a complete operating system, but with the super fine-grained control you need to make it work perfectly for just one job, whether that's brewing coffee or routing internet traffic. All right, so now we know what it is. Let's start peeling back the layers and take a look at how one of these systems is actually put together. What are the core pieces that make it all tick?
To make this a little easier to picture, let's use an analogy. Building an embedded Linux system is a lot like building a custom vehicle from scratch. You're not just buying a car off the lot, you are hand-picking every single component for a very specific mission.
And here are the pieces of our custom vehicle. Way down at the bottom, you've got the hardware. That's the chassis, the frame of our car. Next up is the bootloader, which is like the ignition system that gets everything started. The Linux kernel, that's our powerful engine, managing all the resources. The root file system gives you the interior, the dashboard, and all the tools you'll need. And finally, the application. That's your destination. It's the whole reason you built the vehicle in the first place.
Now let's put the technical names to those parts. The bootloader, which is often a program called U-boot, is our ignition. It does the first-pass hardware setup. Then the Linux kernel, our engine, takes over and manages everything from memory to drivers. The root file system, often built with tiny toolkits like BusyBox, provides the command line and basic tools. And sitting right on top is your custom application, the very reason this device exists.
Okay, the theory is great, but how does a developer actually build one of these things? Let's walk through the actual practical workflow and the tools that make it happen.
You'll see the process is pretty methodical. It all kicks off with setting up your development environment, your toolchain. After that, you configure and build each of those layers we just talked about, the bootloader, the kernel, and the root file system. Once that foundation is solid, then you can develop your own application. And finally, you deploy it all to the hardware and, of course, start debugging.
Now, that very first step, toolchain setup, hides probably the single most important concept in all of embedded development, cross-compilation. And why is it so important? Well, because that little embedded device, it's just not powerful enough to compile its own software. So you do all the heavy lifting, all the compiling on your powerful desktop computer to create a program that can run on that much smaller device.
This right here makes it crystal clear. The host is your powerful PC, where you write and build all the code. The target is the little embedded device, say a Raspberry Pi with an ARM processor, and that's where the code will actually run. You are building on one machine for a completely different one.
All right, enough talk. Let's put all this together and actually see it in action. In this last section, we're going to follow a simple little application all the way from a text file on a developer's computer to a running program on a real device.
So, our goal is super simple, very clear. We're going to write a tiny C program for a Raspberry Pi. All it's going to do is read the CPU's temperature and print it out. Think of it as the hello world for the hardware world.
So how does the code actually work? Well, it's surprisingly simple, and that's thanks to a really beautiful feature of Linux. It often represents hardware information as plain old text files you can just read. So, like the slide says, our program literally just opens a specific system file, reads the number inside, which happens to be the temperature, and then prints it out. No crazy low-level hardware magic required.
And here it is. This is the magic step, the cross-compilation command. We're running this on our host PC, right? We're telling a special compiler that knows how to build for ARM processors to take our source code, cputemp.c, and create an executable file called cputemp that is built specifically to run on the Raspberry Pi.
So after we copy that compiled program over to the Pi and run it, we get this, the payoff. Our program, which was built on a totally different computer, is now running on our target hardware, and it's successfully reading its own temperature. It worked.
So in that really quick example, you just saw all the core concepts in action. We accessed hardware info right from the file system. We cross-compiled code for a totally different computer architecture. We deployed it, we ran it, and we could even take it one step further and use a standard Linux tool called a systemd service to make it run automatically every time the device boots up.
And there you have it. From understanding the big idea of a custom-fit OS, to seeing the layers of the architecture and walking through the developer's workflow, you now have the complete roadmap. This is exactly how those devices we talked about, like that smart camera, go from just an idea to a real application running on a tiny chip.
Embedded Linux gives you an incredible amount of power. It lets you create smart, efficient, custom-built devices to do almost anything. We've just laid out the map for you, so the only real question left is, what are you going to build first?